Okay, let's come back to the lecture. So I understand when you put all the parameters together, it's not easy to understand. But I think because this is the first time you see those equations coming together, so that's quite difficult to understand. But it's okay because we will go through this many times. Because after this, I will give the real numbers, okay, for the design, and you can find out what kind of final results you can, after calculation, you can get from the design, and this gives you a first impression of what kind of range of your sensor can be designed within. And starting from that point, then you come back to your homework, okay? So you can try to arrange the structure again to move the design from the current design you have and toward the final goal you want by changing the geometry. So for you, it's easy, maybe not that easy, it's a simple job. From the equation you have here, try to arrange the geometry, okay, until you got the final result, get into the specs. So the next homework, there will be no standard solution. Everybody can have different solution. Because the design, okay, as long as your final structure, final parameters get into the specs, so all this kind of answer will be correct. Yeah, no only one answer for that question. Yeah, so everybody can have your own special design. But there's still some differences between your design and others' design because we restrict your design inside a small area. So if you can restrict your area as small as possible and also get the highest signal, and that means your design is better than others. Okay? In ICT industry, for example, like Samsung's chip and TSMC chips for iPhone, what's the differences? The speeds, all of the specs, they fall into the specs of the requirement from Apple, right? But end out, you find out TSMC's chips is more efficient than Samsung's chip. Yeah, because they can consume power much less, stay for a longer time, and also not heat up so quickly. Right? So Apple gives them the same specs, but Samsung and the TSMC come up with different, chips, put into your iPhone. So your iPhone have two different versions. You understand? Some chips are coming from Samsung, some from TSMC, but their performance is totally different. So that's why people love to have your iPhone with like a TSMC chips than Samsung's chips. Samsung's chips is not that efficient, although they fit into the specs. So that's why Apple always announce, their performance is within the specs, so no problem. But when you are a customer, you won't think that way. Yeah, you always choose the best product from the market. You never choose the second, best. So that's why for the design, you need to consider from the customer side. Okay, how to make the product the best product in the world, and also the most efficient, less the cost. So that's always the goal to pursue. Yeah, so not an easy task. Yeah. So during the homework in this class, you always can get a 100% score when you design inside the specs. But when you are in the market, it's not the same story. You need to design the best, not only sophisticated products. Understand? Okay. So now we come back to the lecture. Now we understand dynamic range, the upper limit and the lower limit. Upper limit is a strain limit. That means the broken of the system, the sensor. The lower limit will be the sensitivity we just mentioned. You put all the noise together, you got the lower limit sensitivity. Now we consider another important part we call the temperature dependency. So that means all the sensors are temperature sensor. That's good news or bad news, depends on your point of view. You want to use the sensor as a temperature sensor, that's good news. all kind of sensors are temperature sensor. That means they are sensitive to temperature differences. But the bad news is if you want to focus only on one parameter which is not related to temperature, there will be a disaster. Actually, when temperature change also give a signal into your sensor. So that will interfere with your sensing with the real target, for example, as acceleration. Okay, so we need to understand how can this affect your final detection. So temperature dependency coming from one important parameter we call the TCR, temperature coefficient of resistance. That means your piezo resistor has strong effect related to temperature. So you change the temperature, change the resistance as well. Depends on the material you are using. So for example, if we are using metal, okay, as a sensor material, so the TCR, the temperature coefficient of resistance, is represented by alpha here. So that means the resistivity of the metal after the temperature change, delta T times your alpha, the TCR, and then you got the new resistivity. So the relationship is likely is kind of a linear relationship. Okay, so the resistance change linearly with the temperature increment. Increase the temperature, increase the resistance. They are linear. So even they are linear, but they are different in magnitude. So for different metal, you can see the TCR are different. For example, like aluminum is 3.9, and the nickel 6.9. So most of the metal are within the range is around like several times 10 to minus 3 degree K or degree C. So some are a little bit larger, but they are within the same magnitude, same order magnitude. Yeah. So, but they have a different resistivity. Some have a very low resistivity like copper, and platinum has a very high resistivity. So when you are doing the measurement, actually the final resistivity change will be depends on your TCR times the temperature variation. So you have a large rho 0 and a large alpha. Rho 0 is the resistivity. Alpha means the TCR. That means you can get a lot of more resistance change. Okay, so you want to have a very good temperature sensor. You need to choose the large rho 0 and also large alpha for the material. Okay, for example, like platinum is a very good temperature sensor. It has a very large resistivity. The TCR is okay. It's not largest, but it's comparable to others. But it has a large resistivity. So that's why we always choose platinum as a temperature sensor. And also, platinum is very stable in ambient environment. No matter you heat it up or put it inside the oxidant environment. So the material itself is very stable. So that's why you're using platinum a lot as a temperature sensor. But for others, maybe not that stable. For example, like aluminum, copper, nickel, they can be oxidized in ambience. So if we put them into the ambience, it's not that good as a stable sensor. For gold is very stable in the ambient. However, its resistivity is low, very conductive, and the TCR is not that high. So compared to platinum, gold is not as good as a sensor for temperature sensor. Okay, so this is for temperature. However, in our system, we don't want the sensor to be very sensitive to temperature change. We want to operate at different temperature, but with similar output results from the acceleration input. So that's why we want to keep the temperature sensitivity as low as possible. So in our design, we are not using metal as a sensor. We are using silicon. So now we need to consider the temperature dependency of the silicon at different kind of doping, different kind of conditions. So we have 4 figures, important figures here. So now we are starting from the first figure. So for the first figure, we have 2 silicon substrate. One is a single crystal silicon. The other one is a polysilicon. Single crystal silicon means the substrate we are using. Okay, it's a single crystalline. And the polysilicon, that's the material we deposit onto the surface. Okay, so in our CMOS process, currently we are using polysilicon. It's not a single crystal silicon as a sensor. Okay, so you can see the resistivity reduced a lot when we are doping different levels of the impurity into the single crystal silicon and also polysilicon. However, no matter how you dope polysilicon, the resistivity is always larger than the single crystal silicon at the same concentration of the doping. Okay? Because polysilicon has a lot of crystal boundary. Single crystal silicon don't have any crystal boundary. Okay? No grain boundary. So when the electron going through the single crystal silicon, the resistance is lower than going through polycrystalline silicon, because the polycrystalline silicon has a lot of boundary, grain boundary. So the electron going through a lot of boundary that not that easy. It blocks the transportation of the electrons. So polycrystalline silicon, from this figure you can understand, is a higher resistivity when compared to single crystalline silicon. Then we consider the second part, the different doping concentration. So interesting thing is that the doping concentration, the first one is the description method is different from the second one. The description 10 to 16. Okay, 14 to 16. So we are talking about this is a per volume, and the other one is talking about the per surface area. Okay, so the value is different. Please be noticed. Okay, so for polycrystalline silicon, you can see the long axis, the vertical axis represent the resistance change. Okay, so when the resistance change and corresponding to the temperature change, if the slope is negative, we call it a negative TCR. For metal, is alpha. The alpha is always positive. When you increase the temperature, the metal's resistance always increase. But for polysilicon or silicon, when you increase temperature, the resistance decrease. So the TCR is negative. The slope is negative. That's the first one you need to understand. Okay, and when you increase the doping level, okay, so here the first curve you see here is 2 times 10 to 14. When you increase the doping level to 8 times 10 to 14, you can see the curve become flatter. It's not that steep, because it's flatter. So that means the slope is smaller. Okay, and you further increase the doping level up to like 1 times 10 to 16. You can see the curve become positive. It's positive TCR. So that's interesting. So for polysilicon or single crystal silicon, it's possible by using the doping, different doping level, you can adjust the TCR from negative TCR into the positive TCR. Okay? And also for positive TCR, the curve is very flat, similar to zero slope, very similar. And also you can consider, try to lower down a little bit the dose. You can finally get a curve almost no TCR, right? It's possible. So that means it's possible to find out some kind of doping level. The polysilicon substrate is not sensitive to temperature anymore. So it's becoming not a temperature sensor. It's good. That's what we want, right? Okay? So now we see further. So if we want to build up a sensor, so which is better, polysilicon or single crystal silicon? Which is better? So from this figure. The figure has the draw of the TCR of the silicon crystal silicon to polycrystalline silicon. So you can see single crystal silicon, no matter what kind of doping you have, the TCR is always small. So it's very good as for non-temperature sensor. It's not as temperature sensitive 8 more. So it's good. So you can choose any kind of doping level, and the single crystal silicon usually won't give you too much TCR. But for polycrystalline silicon, it's very sensitive to the doping. You can see the TCR change a lot, especially for low doping level. You can see the low doping level polycrystalline silicon has a strong TCR effect. So you want to design a sensor, a temperature sensor. So it's better to use polysilicon than single crystalline silicon, right? Okay. But if you don't want to design this as a temperature sensor, you definitely consider single crystalline is better than polycrystalline silicon. However, if you don't have a choice, like in our class, in your homework, you have polysilicon as your sensor. You have no choice. So how do you design the polycrystalline silicon as a low temperature sensitivity? So we need to consider to give a little higher doping level. For example, doping level when it's higher than 10 to, it's close to 10 to 20. Remember, the unit here is different from the unit here. The unit here is per surface area. This unit is per volume. They are different, okay? So they have like a 1,000 times differences because of the volume, and one is the volume, one is the surface, okay? So when you have a very high doping level of polysilicon, so you can see, actually we can lower down the temperature sensitivity, and even you can get the Z point. The Z point means at this kind of doping level, you got 0 temperature sensitivity for polycrystalline silicon. So you still can do that, okay? You still can do that by using polycrystalline silicon. Just try to adjust the doping level into this position, okay? Now, we consider the last part. So when we try to adjust the doping level from here to here, will this change the piezoresistivity? Piezoresistivity is the character we want to use to design our sensors, a strength sensor. The question will become, can we build up a very good strength sensor without any temperature sensitivity? That's our final question. Okay, so now we look at the last figure. The last figure, you can see for different dosage level. Remember, here the unit become the surface area again. Okay, so actually, if you have this kind of doping level from 10 to 14 to 10 to 16, okay, so the strength sensitivity does not change much. That means the slope does not change much. Okay, but within this range, is it possible for you to find out some kind of doping level with very low temperature sensitivity? For example, like 10 to 16. Here, you already have a very low temperature sensitivity. So the dose level when is a little bit lower than 10 to 16. For example, like 5 or 6 times 10 to 15. You may find a 0 temperature sensitivity material. But in this case, even you have like the temperature, the doping level at like 10 to 15, so it's still within the range of this window. And the slope from 10 to 14 to 10 to 16 does not change too much. That means you can sacrifice a little bit strength sensitivity, but you gain very good temperature on sensitivity, not sensitivity. Okay, understand? This is a trade-off. So that does not change your strength sensitivity too much. The slope changes a little bit, but dramatically reduce your temperature sensitivity as well. Okay. So when you design the strain gauge sensor, you need to understand, try to manage the doping level close to 10 to 16, maybe a little bit lower. Try to make the temperature sensitivity become 0, but still keep the similar strength sensitivity at a high level. OK， 需要用中文讲一遍吗？需要。OK， 好，你现在要 做一个 sensor， 这个是一个压阻式的材料 sensor。压阻式材料 sensor 必须要对 strain 对应力要有感觉，但对温度不要有感觉。对温度有感觉，它变成温度感测器了，这我不喜欢，对不对？那你怎么设计？好，那可以靠调它的 doping level 来达成。好，你看右上角这张图，所以不同的 doping level 对 polycrystalline silicon， 你可以调到一个doping level 是几乎是没有对温度是不敏感的，好，对温度是不敏感，这是温度的变化。那这 slope 呢，就表示它的 TCR， 啊，就它的这个斜率。斜率越高的话呢，它 TCR 越大。像这条线呢是负的 TCR， 它斜率是负的。你调到，因为它是比较低的 doping level， 你调到比较高的，像10的负16次，10的16次方的时候，它变成正的 TCR， 好，就是它的这个斜率变成正的。正跟负的差别就是，你增加温度的时候，阻值会增加还是减少？负的 TCR 是你温度增加的时候，阻值会减少；正的 TCR 是你温度增加 ，TCR 就是阻值会增加。金属全部是正的 TCR， 没有负的。好，只有这种半导体的材料才会很奇怪，有时候负的，有时候正，这跟 doping level 有关系。好，那我现在这边看得到，我可以找到一个 doping level 是完全没有 TCR 的，这 good， 非常好。那但是这个会不会减损我的能力在这个 strain 的这个量测上？这我就要考虑了。如果会减损很大的话，那这个就不是好 sensor， 对不对？所以我回过头来检测，从10的14次方到10的16次方，确实对 strain gauge 来看的话呢，它的斜率会有一点点变化，但是变化不大，有没有发现？好，10的14次方斜率是比较高的，16次方斜率稍微低一点，但它的变化呢可能在20% 左右，所以这个其实我可以忍受的，所以我牺牲一点点 strain gauge 上的敏感度，好，但是我要达成对温度不要敏感，所以我就把我 doping level 接近10的16次方左右。好，所以10的16次方左右，它的 TCR 是正的 TCR， 而且是很小的。那但是这时候呢，我可以达到一个还可以的 strain 的这个敏感程度。再了解哈，所以通常设计 sensor 没有那么简单呐，所以你一个 parameter 设计好就好了。事实上它还有其他的 side effect 会跑出来。好，温度就是其中一个很重要的一个部分。所有的 sensor 都是温度 sensor。好，很少数的材料是对温度不敏感的。好。那现在用来我们做我们手表那个 quartz， 各位知道那个石英，为什么用石英来做那个振荡器？主要是石英的温度系数很低，对，要不然你戴的手表一天都不准，一天到晚都不准了。你像今天比较冷，对不对？就跑比较慢，对不对？前几天又跑比较快，那怎么会准呢？问题在这里，啊，这是在设计sensor很困难的地方，温度的这个敏感度。好，那这边告诉你可以靠着 doping level 调整，可以把这个参数调得比较适当一点。Yeah, we just repeat the information in Chinese. Sorry about that. Okay. So yeah, so it's important to understand. To design a sensor, it's not only one parameter. We need to consider all. So if you have a very strong, very good sensitivity to strain, that does not mean the sensor is not sensitive to temperature as well. So you need to consider them at the same time. Okay, both of them at the same time. Try to reduce the temperature sensitivity, but try to maximize the strain sensitivity at the same time. Okay. Yeah, so that's a basic idea. And then how to compensate the temperature effect? Actually, it's a more advanced topic. It's beyond the scope of the course, but I just mentioned several you can consider. The first one, we can try to cancel out the temperature variation, the effect, by design the resistor as a symmetrical arrangement, like a Wheaton bridge. In the Wheaton bridge, you have 4 resistors designed on a circuit, right? So when the temperature elevates, all the 4 sensors, the temperature can be elevated as well. So the increment of the resistance can be cancelled, okay, from one to another. Okay, that's one way. But still, the environment is not that the same. Actually, not that similar. Consider some of the resistors sitting on the top of the cantilever. Some are sitting on the silicon substrate. Okay. So when you heat up the substrate, actually the cantilever part, the temperature will be higher than, the second part will be higher than your cantilever part because cantilever has some heat transfer problem. So it's not easy to transfer heat from outside to inside or from inside to outside when your sensor is sitting on the top of the membrane of cantilever beam. So there's still some temperature differences. So that's why people need to arrange different kind of even more difficult structure, more than Western bridge. When you look into the literature, actually some people design some complementary circuits like a extra resistance besides the sensing resistance, try to cancel the temperature effect. But the symmetry design is one way to cancel the temperature effect. But the symmetry design cannot cancel the noise. No. Noise is always there. When you increase the number of resistance, remember, you increase the noise at the same time. Even you can cancel the temperature effect, but increase the noise. That's a side effect. Yeah, so design is not easy. The second one, you can do feedback control. Okay? Try to measure the temperature from the other circuit and try to cancel out this effect and by reducing maybe the current going through the sensor. So this is feedback control. It's a more complex algorithm. Or you can do it outside. You do the calibration of a temperature curve, and by using software outside, you can do outside calculation and bring back the original signal when we deduct the temperature effect by using calculation later on. Okay, so there's 3 different ways to compensate temperature effect, but not easy. Okay, so those important parameters we have described and also explained. In the future, maybe you need to consider another part of the sensor, including the long-term stability regarding the operation lifetime, unshaped life, long-term drift, those kind of things, which may happen on the sensor. Because that depends on the materials. Some materials, they cannot be operated for a long time, and some cannot become stable for a long time. So they need to be taken into consideration as well. So that's why when we are using a sensor, it's not only calibrate inside the factory. When it's outside the factory, you still need to find a way to do the calibration sometimes. For example, like every 1 week or 2 weeks, or maybe 1 month, you need to do the calibration. Try to find back the curve. Because sensor always have some kind of drifting problem. Yeah, 所以就是 sensor 它的讯号会跑掉。你出厂了以后，它不是会跟你的厂里面会完全一样，所以常常都需要校准 ，calibration 需要校准，然后把那个曲线再找回来 ，OK， 所以这里都是 sensor 会遇到一些实际上的问题。